So my name is Tomasz Janczuk. I work for Auth0, and I'll be talking about the journey that has taken us to using CoreOS, Docker, Fleet, etcd, and all that goodness. I'm currently working for Auth0. This is by far the best job I ever had, and that includes prior career at Microsoft and HP. We started our trip to CoreOS and Docker Fleet by looking at the client-server architecture, something that dates back to the 60s. And most modern mobile and web applications are really based on that architecture. If you look at the role of client-server architecture, it really serves two purposes. One is to reuse common resources on the backend across several clients, and also to create a trust boundary between the client and the server. For example, if you want to access a MongoDB database or send an SMS via Twilio, you would embed that logic on the backend and therefore protect your keys that grant access to that backend system. So in a typical interaction, the client would send a request to the server, provide some client data, the server would crunch this using those protected resources and send back the response to the client. Since trust is really an identity is at the core of what my company is doing, we had a really hard look at the trust aspect of the server. Specifically, we have taken the server code and secrets that constitute the core of the application logic on the backend, and we extracted it from the server. So now we have that bundle of server code and secrets, which is just data. And given that this is data, it can be cryptographically signed and encrypted. So we call that bundle a Webtask token. And this really represents your application logic that normally executes on the backend. So further, we take the code and put it where code belongs, S3, GitHub, some place in the cloud that can be referenced with a URL. And instead of storing the entire code in that Webtask token bundle, we store just the URL. So the bundle becomes really small and yields itself very well to be passed around on top of a variety of protocols, including HTTP. So this is a typical size of a Webtask token that contains URL to the server code and some secrets like MongoDB connection string or Twilio keys. Given that this is cryptographically protected, it is okay to pass it along across untrusted channels, and it is also okay to put it directly in the client application. So you could theoretically take that Webtask token and ship it as part of your mobile app or single-page web application without the fear that your MongoDB connection string or Twilio keys will be compromised. So what can the client do with that bundle? It can tack it onto the request that it was normally making to the server. The request still specifies the client data, but in addition, it also instructs the server what kind of logic to execute. So that Webtask token specifies the server code to execute, as well as the secrets the server needs to run that code. In this case, it could be, for example, access to a MongoDB database. So it is interesting to look at this point at the role of the server. The server now became a very generic code execution engine. At a very high level of abstraction, the server basically accepts an HTTP post request that tells it what code to execute. The server will execute that code and return the result back. So we have moved off of very application-specific backend to a very generic backend that can accept any Webtask token and execute it. The programming model for that thing is very, very simple at heart. It is quite similar to the Node.js HTTP handler. So it basically accepts a request and a response, and in addition, it takes a context which specifies the secrets and all the data that was present in the Webtask token. We have implemented a a playground around this concept, Webtask.io. You can go ahead and play around with this concept, see how it works in practice. But here I would like to say a few words about how we have gone about implementing it. Implementing that generic server for the sake of just one application is a relatively simple affair. You just accept code. In this case, it is Node.js code, so you can just eval it in process, return the response, and you're done. Doing the same thing, implementing that server for a multi-tenant, as a multi-tenant platform, which can accept any code, potentially untrusted and harmful to other tenants, is quite a different challenge. And this is what we have set off doing at Auth0, because this is actually a core part of our identity management infrastructure, which is extensible through custom code. So this is where CoreOS, Docker, Fleet, and etcd come in. At the single VM level, when a request to execute server code arrives on our machine, it ends up at the proxy component. The proxy will determine if a container associated with a tenant making the call is already provisioned in the system, and if so, it will reverse proxy that request to that sandbox. If such a container doesn't exist yet, the proxy will actually fetch a pre-warmed container from a pool that we maintain at the CoreOS level. The reason we have done it that way as opposed to just spinning containers on the fly is that Docker containers are pretty quick to create, but they were not quick enough for us. It still takes several tenths or hundreds milliseconds to spin up a container that runs some software that allows you to execute arbitrary Node.js code. So we are maintaining a pre-warmed set pool of containers, and basically when a request arrives to execute code on behalf of a tenant that we haven't yet seen, we just pick an unassigned container from that pool and execute that code in that container. Going forward, we store the configuration of that association of a container to a tenant in etcd. So for subsequent requests, if they arrive, we just pick a pre-assigned container based on the information in etcd and reverse proxy that request to that container. So this is what is going on at the level of a single CoreOS VM. Now the first layer of high availability, before we go there, in addition to executing code, we are also enabling people to debug that code very easily. So if you, for example, embed a console log in your Node.js code that you are executing, the question is how do you get it back as a developer out of that cluster? And to support that functionality, we are actually deploying a Kafka cluster, including Zookeeper, into the CoreOS cluster. And we are using Kafka as a mechanism to collect logs from all the containers and surface them out also over HTTP to consumers in a streaming way. So basically, you have access to streaming logs, real-time logs that the code running in the container generates on your behalf. So this is the story at the level of a single VM. High availability is kind of high order bit for what we do in Auth0. So the next level for us was to kind of design high availability features into this deployment. The first level of that was deploying a CoreOS cluster. So that CoreOS cluster consists of several of those VMs that I just shown with an ELB in front of that cluster. In addition, these VMs are scattered across different availability zones inside of a single data center in AWS and deployed on different private networks, access to which from the outside is only possible through two NAT boxes. The NAT boxes also ensure that any egress traffic from those containers will present a uniform set of public IP addresses to the outside world. So for example, if you are running code in the sandbox that is connecting to your on-premise MongoDB database, you can configure firewall rules in your enterprise to allow only a certain set of incoming source IP addresses that are well known in advance. So that is the first level of high availability, basically a single CoreOS cluster. But given that our high availability requirements are higher than that, we also have a failover built into the system. So we have actually two such clusters, one on the West Coast, the other on the East Coast of the US. And we have a traffic manager, Route 53, configured in front of the two load balancers of the two clusters, such that one cluster is always acting as a primary cluster and the second one is acting as a failover. So if there is an earthquake in San Francisco and the AWS DC goes down on the West Coast, we will just switch over to the East Coast. And we have a very similar deployment in Europe. So as I said, you can go ahead and play with that Webtask.io concept on Webtask.io site. It is completely free. So basically what happens is you can type in any code you want here, and it will execute on the right via Ajax. And as you notice, it was pretty quick. I can say whatever I want here. San Francisco. And it's 344 milliseconds. It's only because it's going through my phone right now, because the Wi-Fi is not as quick as my phone. So feel free to go and experiment Webtask.io. Tell us what you think. This is a very early stage for that concept. We think it is a very exciting way of thinking about your backend functionality. We have many more examples on that side that show things like access to MongoDB or processing Stripe payments or sending Twilio messages or sending email directly from your mobile application or single-page application without the need of deploying any backend on your own. So you're basically making an HTTP call with a Webtask token embedded in it, and that cluster takes care of the rest in a way that is isolated, secure, and quick. So this is how we are using CoreOS and Docker to use. Thank you.